Good morning, students. Today we are going to see evidences for crystal field stabilization energy. In last lecture, we see there is the splitting of d orbital or d energy levels of the metals, and that splitting will be get stabilized. The crystal field stabilization energy plays an important role in the thermodynamic properties of transition metal complexes or compounds. Many complexes of transition metals are stabilized due to CFAC. Transition metal compounds and the complexes of weak ligand with D0, D5 and D10 system metal ions have no crystal field stabilization. These compounds show regular gradation in the properties like lattice energy and heat of hydration. However, the transition metal compounds having the configuration other than D0, D5 and D10 show the irregularities in these properties. When we have the plot of lattice energy of dichloride ions of the metal ion from zinc to calcium, and another plot heat of hydration of divalent ions of the metal from calcium to zinc, it shows, see, their CFAC is calculated here in the table D1 system to the D10 system. We having the for D1 system CFAC is minus 4 dq, D2 minus 8, D3 minus 12, D4 minus 6, D5 system 0 CFAC, D6 system having minus 4 dq plus 1 pairing, D7 system minus 8 dq plus twice pairing energy, D8 system minus 12 plus 3 pairing energy, D9 minus 6 plus 4 pairing energy, and for the D10 it have the 0. When we consider the strong field, in the strong field there is the particularly D1, D2 and D3, they have the same CFAC. For D4 it is minus 16 dq plus 1 pairing. For D5 it is minus 20 dq plus 2 pairing. For the D6 it is minus 24 dq plus 3 pairing. D6 minus 18 dq plus 3 pairing. D7 minus 12 plus 3 pairing energy, and for the D9 minus 6 plus dq plus 4 pairing energy, and for the D10 it is 0. See, it is reflected in the first, that is the 7.6 figure. See, lattice energy of the dichlorides of the elements from calcium to zinc. It shows that the D0, D5 and D10, they having the points on the straight line. As it is expected, the lattice energy should be gradually increases, but it shows the particular line D1, D2, D3, D4, D6, D7, D8 and D9. They show the points above the graph. That is there is the increase in the lattice energy. When we have the such type of the graph, or the actually figure of the lattice energy is higher than the expected, when we can have the minus, we can minus the CFAC from the total figure of lattice energy, then that points will be lie on the straight line graph. This indicates that this D1, D2, D3, D4, D6, D7, D8 and D9, they have the crystal field stabilization energy which will be shows above the graph, above that particularly expected point. Similarly, when we calculate the heat of hydration of the divalent ions from calcium to the zinc, calcium having the D0 system, Mn having the D5 system, and Z zinc 2 plus have the D10 system. See, again similar points will be repeated here. We having these 3 points on the straight line, and another ions they have the points above this line, expected line, and we can have the particularly higher figures. When we minus the CFAC of that particular ion, it will be get, or that point will be lie on the straight line. This indicates that these ions have the crystal field stabilization energy. These these are the energies of the process, that is M plus M2 plus 6 H2O. It gives the MH2O6 aqueous. The observed energy are shown by the circular points in the graph. It is seen that the smooth curve, which is almost the straight line, passed through the points for 3 ions, that is Ca2 plus, Mn2 plus and Zn2 plus, which have no CFAC, while the points for the all other ions lie above the line. On the subtracting CFAC from each of the actual lattice energy or heat of hydration, we will get the points which will fall on the smooth curve. These observations provide the evidences for the crystal field spectra and measurement of 10 dq or delta O. Study of the absorption spectra of complexes enable us to find the values of delta O or 10 dq. A band or bands in the absorption spectra can be related to the excitation of an electron or electrons between the orbitals, that is DD transition, split by the crystal field. The ability to interpret such spectroscopic evidence is one of the advantages of crystal field theory. Consider the octahedral complex ion TiH2O6 3+. It offers a simple case, that is, it has only one d electron. In the ground state, the electron will occupy one of the T2g orbitals, but absorption of radiation will excite it into one of the EG orbital. Thus, for a D1 ion, only one transition from T2g to EG is expected. The difference in energy between T2g and EG is delta O or 10 dq. Figure shows the absorption band due to DD transition in H2 TiH2O6 3+ complex ion. See here, it has the molar absorption, and we having the plot of molar absorption versus the particularly frequency, and we can get the such type of the spectra which having the wavelength, and we having the particularly visible absorption spectrum for this complex. See here, when there is the T2g and EG, there is single electron in T2g orbital. When it will be get excited, it shows the single electron in EG orbitals. At that time T2g orbital is vacant. So both the figures below figure that shows the DD transition in TiH2O6 2+ ion, and that particularly the difference between T2g and EG is the 10 dq, and we having the absorption spectra of the same wavelength, and we can have the spectra of that particular compound. The absorption band shows a maximum at 20,400 centimeter inverse. Energy is equal to h nu is equal to hc nu. H is the Planck's constant, it has the value, c is the velocity of light, v is the particularly wavelength, and substituting these values, we get the energy 10 dq or delta O, that is the 4.045 into 10 raised to minus 19 joule mole inverse. To find out the energy per mole, we multiply by Avogadro's number. So 4.05 into 10 raised to 19 minus 19 into 6.023 into 10 raised to 23 joules mole inverse. We get the 244.2 kilojoule mole inverse, that is 58.35 kilocalories mole inverse. Thus delta O is equal to 244.2 kilojoule mole inverse, that is 58.35 kilocalories mole inverse. Light of frequency Light frequency 20,400 centimeter inverse is green. If such a light is absorbed, the transmitted light appears violet, and hence TiH2O6 3+ ion appears violet. So it is the transition. Due to the DD transition, we know that all D block elements compounds can shows the color. Thus here titanium, this aqua complex shows the violet color. It is the complementary color to that of the absorbed light. Let us consider another example of absorption band due to DD transition in CrCl6 3- complex ion. At this complex ion at 13,640 centimeter inverse, let us find out the value of 10 dq or delta O in this complex. See, energy is equal to h nu h c nu. So h is the Planck's constant, c is the velocity of light, and v is the 13,640 centimeter inverse. Substituting these values, we get the energy is equal to 10 dq or the delta O. See, after filling all that figures, 6.624 into 10 to the 34 into 3 into 10 to the 10 into 13,640, we get the 2.71054 into 10 to the 19 joule mole inverse. To find out the energy per mole, we multiply by Avogadro's number, we get the 163.26 kilojoule mole inverse. By converting it into the kilocalories, we get, that is the kilojoule into kilocalories, we get the 39.2 kilocalories mole inverse. Light of frequency 13,640 centimeter inverse is red. If such a light is absorbed, the transmitted light appears bluish green, and hence CrCl6 3- complex ion appears bluish green. With complexes containing more than one d electron, the transition energy changes between the d orbital becomes more complex, and the resulting absorption spectra contains more than one band. They can nevertheless open the interpreted to give the 10 dq values. The absorption spectrum of NiH2O6 2+ ion, for example, shows the three bands, which can be accounted for if delta O is taken as being equal to the 101.7 kilojoule mole inverse. If it follows that when the energy of the absorption is in the visible region, then only the complex shows a color.